All right, one of the major things that you're going to learn to do in this class is annotate genes. It's a major component of your grade, and it's going to increasingly become more important in your research because we have so much data. We have, to this point, relegated the task of annotation to computers, but we're finding very quickly that the computers get it wrong. They get it wrong a lot, and there is a need for individuals to actually go back and annotate the genes by hand, so to speak. I've given you a worksheet here on how to annotate a bacterial gene. Now, understand the bacteria, the regulation of a bacteria or a prokaryote or an archaea, uh, it's different than a eukaryote. All right. The genes are structured different. They're in what are called operons. You will need to know to do this assignment how operons are structured. There are several videos out there explaining an operon. I'm going to do the inducer gene that is, some would say, outside the operon. I include it as part of the operon. But I'm going to do this particular gene as far as annotation for you. You're going to need to do, as an assignment, the rest of the operon. All right, now I have some rules here that we're going to be going by. All right, now also understand that if you are familiar with transcription and translation with eukaryotes, you know that the RNA is created and then it leaves the nucleus and out in the cytoplasm, it attaches to a ribosome and translation occurs. In bacteria, it's a little different. In bacteria, the ribosome attaches to the RNA actually while it's still being created, and several ribosomes can attach to the RNA while the RNA is actually being transcribed. It attaches at several places. All right, it attaches at something called the Shine-Delgarno sequence. All right, so you can actually have a transcript with several ribosomes attached to it, and usually they attach at what is called a Shine-Delgarno sequence. So this is a great place to start for annotating a bacterial gene. So let's take a look at the sequence here that the ribosome attaches to. The consensus sequence is AGG. Now, as you might guess from some of the other videos you've watched and some of the readings, that this isn't the only sequence that a ribosome can attach to. It actually varies quite a bit. Just because this is a consensus doesn't mean this is the one you're going to find all the time. You're going to have to actually kind of look around and see if you can't find something similar in the right area that the ribosome might attach to. And here we give some hints that commonly sequence AGGA or GAGG. In general, you're going to find that the ribosomal binding site, all right, is AG rich. But that's about all we can say. You're just going to have to realize it's 3 to 13 base pairs upstream from the start codon. So in the assignment you have, we already have looked at the GenBank file, and it tells us where the coding regions are. So here's our methionine. This is where our AUG will be. And we know that that AUG here on this sequence is at 70. So if I go back over here to my FASTA file, and here I have done something I told you not to do. I have used something other than a basic text editor to format this FASTA file. Realize if you do something like this, this type of formatting is going to alter your FASTA file, and several programs that we might use are not going to be able to read it. And so what I've done, I've taken the GenBank file, and I've used the fact that it starts at 70, it tells us this, and ends at 1161. That's the region that codes for this particular protein, which is what I'm going to help you annotate here. You're going to have to do in the assignment the other 3 proteins here. So I'm going to look for something before, all right, the The start codon, which I've identified here, if you can see it's in red, all right, that's the start codon, and here we have it. Here's the stop codon. Now realize, of course, GTG or GUG is what this would be representing in a FASTA file, is not your standard start codon. AUG is, but GUG obviously works in this case for this particular organism, all right, and for this particular sequence. Again, this is a reason you can't just have a computer program go through and look for standard sites. You actually have to have a person will often look at this and look for things that are close. Some people are trying to write programs that can do this for you, and they are having mixed results. So often you do have to have a person actually go back and look at these sequences, and that's one of the reasons we're going to be doing our annotation with the GEP, which I will explain in another video. So if this is our start and stop codons, this is our coding sequence, what would we look for before that? Well, before that, we need a transcription factor maybe, and a Shine-Delgarno sequence. So, I'm sorry, not a transcription, a promoter in our that will bind here to the TATA box. We need this up front. Let's see if we can find any of these sequences in the region we have here. Now realize these things come before the transcript that's made, and this is supposed to be the transcript, the RNA. So you might not think that you're going to find any of these in here, and we very well may not. However, I'm going to have you read an article that's going to show you that we're now finding that even in bacteria, there's a lot of variability, and ribosomes and polymerases can attach in very odd places and in multiple places, even in bacteria. It's often been thought that there's only one promoter per gene, and generally we're finding that that is not the case, even in bacteria. So we're going to kind of look at this piece right here, this region in here. We're going to see if we're going to find anything interesting in here. Specifically, we're going to look to see if we can find a Shine-Delgarno sequence, or maybe even a TATA box. So I'll start with our Shine-Delgarno sequence, but I'm not going to start with this big one. I can tell you right now that's not going to be in there. But we might find something like this or this. So I'm going to look up things with G's and A's. I'm going to search this sequence, all right, for G's and A's, and we're just going to see what we can find here. So in this region, all right, I'm going to look for GA. Actually, it searched the whole thing, but as you can see here, here are a lot of GAs. All right, let's see if this is any different, if I get anything different with AG. And still, this region and this region, but this looks like this has the potential for being a Shine-Delgarno sequence. Now, when you do this assignment, you're going to say, well, I didn't find the exact sequence you said look for. I'm not going to count off for that. I want you to make a argument that this sequence is a Shine-Delgarno sequence. It looks like a good place for a ribosome to attach and actually perhaps start doing translation. Why not attach here? It's before the start codon. There's no reason it couldn't be a functional Shine-Delgarno sequence. And if you look at our requirements, really, it just has to be AG rich. All right, it's generally about 6 bases long. We have some GAs, some AGs. Those things are in there. I think there's a pretty good argument that this is a Shine-Delgarno sequence. There are GAs. There's a GAGA, a GAAG. All right, it isn't exactly like we see, but I would make an argument that there's a good chance that this is indeed a Shine-Delgarno sequence. And it says it needs to be 3 to 13 base pair upstream from the start codon. Well, let's see if that's the case. So let's find our start codon. Here it is. And so 3 to 13, so I'm going to go backwards by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Hey, we are right in the range for this to be a Shine-Delgarno sequence. I think that's a Shine-Delgarno sequence. So this is the kind of justification I want you to make when you do this assignment. You look through and you're going to look for these features and you will make your argument. Now, I'm not going to count off if you are wrong necessarily, in the sense that it's been proven maybe in some research paper that no, the ribosome does not attach to this sequence. I want you to make a good argument based on what you do know. And I'll be grading you on how good of an argument you make. Basically, this is probably a Shine-Delgarno sequence, and I think we can make a pretty good justification in that even though we don't have the consensus here, we have an AG-rich region that is between 3 and 13 base pair before our start codon. I think that's a Shine-Delgarno sequence. Now let's look at our promoter sequence, our Tata box. Now a Tata box or a Prinbout box usually is at minus 10. That means 10 base pairs upstream from the transcription start site. Now, normally that might mean if this is the start of transcription, that means that it would be 10 maybe before this. But we're finding that promoters actually can be found all over the place, even in the middle of genes. And we have alternative versions of even bacterial genes. Now, we know this for quite a while that this has been occurring in eukaryotes. But now we even know, I'm going to let you read a paper, where we believe it's occurring in prokaryotes as well. All right, so let's look here. If this is your Shine-Delgarno sequence, is there anything that looks like a Tata box? T-A-T-A. Not really, to tell you the truth. Nothing offhand. Here's a TA. Here's one. All right. TAT. Well, you never know. That might be a thing. You could make an argument that this is a Tata box. Here's a TAAT. There's a G stuck in there, but you know, that looks kind of like a Tata box. TAATA. You have a G here instead of an A, but that might be acceptable. Let's go back and look at our requirements here. Our requirements are that it needs to be between minus 8 and minus 13, or here's another version of it at minus 8 to minus 13. Where is minus 8 to minus 13 compared to transcription start? Well, if this were we know that this AG-rich region needs to be in there. So transcription start needs to start, say, in this region. So we know that has to be in there. So let's go backwards about 8 and see what we get. So 1, 2, 3, 4, 5, 6, 7, 8. So if transcription started up here, you could see this right here as a Tata box. All right, that could be your attachment place for the polymerase. That would give you enough room for transcription start to start here. That would be a nice starting place for our ribosome to attach, which actually is at the end, so it would actually be very similar to what happens with a eukaryote, which always attaches to the 5' end. So all of this could work. This could be a Tata box. That could be a Shine-Delgarno sequence. Here's our start codon, and here's our stop codon. So this is the kind of argument I would like you to make, but I want you to do it with the other three. And I will give you a worksheet, and you're going to have to write basically where in the sequence you think this is. Now, the hard part for this is where are all of these things? Well, this is 70. You can look through these and realize this is 70, so this is going to be 140, 210, etc. Each of these lines is 70 bases long. All right, so you can count up where exactly your sequence is. You could also go back to your, where is it here? um, to your GenBank file, and that might help you find your exact location when you're telling me where these things are. So what types of things are you going to be looking for? You're going to be looking for Shine-Dalgarno sequences, start and stop codons. That should be easy. You can use your GenBank file. You also need to look around for termination sequences. I didn't go over termination sequences, but there's a pretty good description here of how they work. And you may not find them. There's also a promoter region, which is your TATA box. There are other promoters besides TATA and bacteria. There aren't many, though. Here are some other sequences you might look for. Now, these things are not common in E. coli. Well, I shouldn't say they're not common, but flagella aren't. But there are other genes. This particular gene probably is going to use a TATA box, and the lac-operon would be more likely. So you don't have to worry about it, but you might look for these. It doesn't mean that they couldn't be there. All right, so I'd like you to do that and annotate that gene. I will be giving you a more detailed written description of the assignment, kind of like where is it located. I'll give you a place to put the location, and then but majority of your grade will be based on your argument as to why that is there. And that is our recording for this assignment.